Okay. Okay, so we now change perspective. So we shift from longitudinal to transverse polarization. And we enter the world of chiral objects, like the transverse distribution. And in the title, I deliberately remind all of us that the extraction of transversity, if you go back to the original EIC white paper, was ranked as a singular measurement. So interestingly, if you look at the document, you see that for each physics topics, there is a table with the key measurements identified. But only for the TMD case, there is a ranking, speaking of golden and silver measurements, not in the other cases. And curiously enough, I didn't find any reference to the bronze medal, so only gold and silver.
So the bronze is G2 measured in physics.
Okay, but it was not written explicitly, at least. Maybe understood. Anyway, so there are at least two obvious, very good reasons why we want to extract transversity. The first one was already recalled by the previous speaker, is that transversity is the third member of a group of 3 collinear PDFs that are needed altogether to have a complete description of the spin structure of nucleon and in general all the spin 1/2 objects that lead into waste. And the second good argument is that it is a chiral object, so it could be a doorway to explore novel QCD dynamics. Also, when transversity is considered as a TMD, not necessarily as a PDF. But there is another third good argument that probably was not clear at the time of the EIC white paper, and has to do with the first moment of transversity, which is called quote tensor charge. I put quotes because it's not a conserved object quantity. But in any case, it is connected to an operator, the tensor operator, which does not appear in the QCD Lagrangian, at least at 3 level. So it could be, again, a tool to explore new physics beyond standard model. So exploration of this new physics can happen in different ways. For example, if you stay a very large energy, you can directly search for evidence of new particles. Okay? But if you have enough precision, you can go to lower energies and look for indirect evidence induced by these new particles. And if your precision is really very high, you can even look at footprints left by these indirect evidences through new effects induced by local operators. For example, in semi-electronic processes, these new local operators dimension 6 local operators can involve 2 fermions or 4 fermions. And the typical example is the 4 fermion interaction, which is a reminiscence of the W exchange in the weak charge current interactions at larger energies. Now, an example of this class of exploration, direct access, is this exercise done by the Atlas collaboration at LHC, where they looked at the data at square root of S of 13 TeV, and they considered a final state made by a lepton and a neutrino. For example, this is the electron-neutrino final state, and they looked for if it is possible to consider these final particles as the decay product of the new heavy partner of the W, so a so-called W prime gauge boson. And here you see the exercise, you see the observation with respect to the expected background from experiment, and it crosses the line of the theoretical calculation exactly in this point, which puts a lower limit of the mass of this W prime, which is slightly above 5 TeV at a 95% confidence level. And this puts in turn constraints on the possible operators that can be active beyond the standard model, among which, for example, scalar and tensor interactions. And the PMDME guys of the lattice collaboration did this exercise and studied which are the constraints induced by this finding on the combined plot of the scalar and the tensor couplings. And you see that the constraints in this blue circle here. Okay? And if you do the same exercise looking at the final state of made of lepton and anti-lepton, and you think that they can come from the decay of a Z prime partner of the Z boson, then you put additional constraints and the circle becomes this red one here. Probably you can't read the scale. Here is 10 to the, from minus 10 to the minus 3 up to 10 to the minus 3. And here between 2 10 to the minus 4 up to 2 times 10 to the minus 4. So it's really very tight constraints on the size of this couplings. Okay, now examples of the other class of exploration, so indirect access. So you can, for example, look at the neutron or nuclear beta decay. And in the cross section, there are terms of the angular distribution, the elicity flip terms that are sensitive to the interaction between standard model operators and possible new operator, dimension 6 operators, including the tensor operator, for example. And if you want to use the data from beta decay to constrain the coupling, tensor coupling, you need to know the tensor charge, depending as the form factor of the tensor operator that you will consider. And the precision of the data set the scale of this possible physics, which is in the PV domain, but also require also a very precise determination of the tensor charge. Now, currently, the beta decay experiments precisions are in the ballpark of 10 to the minus 3, the relative precision, and they are aiming to go even below in few units times 10 to the minus 4. So we really need to have a good knowledge of the tensor charge. In this case, this is a transition between a neutron and a proton, so we are involving the isovetor component. But there are also other examples where we involve directly the single flavor components of the tensor charge. For example, if you look at theories that incorporate the CP violation coming from the electric dipole moment contributions of the Fermi fields of the theory. Again, the deal is the same. For example, you can use experimental determination limits on the neutron electric dipole moment to put constraints on the quark electric dipole moments that give you the size of the CP violation. But in order to do this, you need to know precisely each single flavor contribution to the tensor charge. Now, on the lattice, the tensor charge can be directly computed by calculating the hadronic matrix element of the local tensor operator. As I said, for the phenomenology, you need to extract transversity and on the largest possible X range, and then compute the first Marie moment in order to get to the tensor charge. Now, since the transversity is a chiral object, we have to look for processes where we have a chiral partner of transversity and possibly a leading twist. So the simplest, most obvious choice is to consider transversity a partner of itself, which would lead us to consider the fully polarized Rayleigh process, which unfortunately at the moment is not available. So the traditional way to extract transversity to look at the Collins effect in the single hadron inclusive production, where you have a transversely polarized quark that fragments in a single hadron. And in this business, the chiral partner is the so-called Collins function, and it's crucial to keep memory of the transverse dynamics of the partons. So we work in a TMD framework, and the transversity here is extracted as a TMD. Okay. Alternatively, you can consider the fragmentation of the transversely polarized quark directly into a pair of hadrons, so this is called di-hadron mechanism. Here, the chiral partner is called IFF, interference fragmentation function. And we work in a collinear framework. And now the transversity here is extracted as a PDF. And there is another mechanism which popped up recently. We heard from Elke's talk. It is called hadron inject mechanism, where you basically consider the Collins effect in the final state, but you extract the transversity as a PDF, collinear PDF. So this mechanism is somewhat a hybrid between the two. Okay. In my talk, I will discuss this technique to extract transversity, but when I will come to results, particularly about the tensor charge, I will systematically compare with the results using the Collins effect and with lattice. Okay. Now, which are the advantages, the pillars of using the di-hadron mechanism? Again, is to work in a collinear framework. It means that you don't have to convolute the transverse momenta here. You just have products of collinear PDFs, and in this case, the parallel IFF. For example, this is expression, the analytic expression of the semi-inclusive DIS single spin asymmetry, where you see that you have a flavor sums of PDFs times the di-hadron fragmentation functions in the numerator and in the denominator. So the immediate conclusion that you draw from this expression is that the X dependence of this single spin asymmetry is entirely driven by the X dependence of the PDFs. Okay? and you can integrate about the other variables. And since at tree level, at least, the di-hadron fragmentation function enjoy happily symmetry properties, for example, with respect to isospin transformations or charge conjugation, you can break this flavor sum easily. But thanks to the fact that we have data on proton and neutron targets from compass, we can come easily and cleanly to the separation of the valence up and down contributions of the quark, of the transversity, sorry. Okay, so the next important feature of this di-hadron mechanism is the fact that working in collinear framework, we can use factorization theorems in all our processes. So indeed, we can perform a global fits of all processes, semi-inclusive EIS and the proton-proton collisions, and test the universality of this mechanism that pairs the transversity to the IFF. Now, we have data for all these processes from Hermes compass, as I said, from Bell for the plus minus, and from Star for the proton-proton collisions. So what I'm showing you in the next slides, I didn't use all of them. Some of them are very recent, so I'm planning to get an updated version of my fit, including also this data. For the moment, I will use the data from Hermes and compass on the semi-inclusive EIS on proton and neutron target, only the azimuthal asymmetry data from Bell, plus minus, and the star data in proton-proton collisions from the round 2006 at S equal to 100 GeV squared. Okay, so this is the x q square phase space of the data covered by the data I'm considering, and you see that the range in X is not very large, so realistically we are able only to extract the valence components of transversity. We have too few data going into the low X regime in order to have a reliable extraction of the sequel contributions. And this also impacts our calculation of the tensor charge, because we have to make assumption to extrapolate our results for very low and very high values of X. And this brings me to discuss which is our functional form that we use to perform this fit. So the starting point is that we want to fulfill the Sofer bound always. So we start from the analytical expression of the Sofer bound at some starting scale, Q0, and we build it using the M3W parameterization for the unpolarized PDF and the DSSV parameterization for the Radici. And for the moment, everything is done in leading order, just to keep things simple. And again, work is in progress to improve it. Then at this scale, initial scale, we take this analytical expression and we multiply it by a functional form, which is just a linear combination of Chebyshev's polynomials in order to have some degree of flexibility as a function of X. As I said, we are considering only valence quarks, so we have in total 10 three parameters, 5 for the valence up quark and 5 for the valence down quark. And the question is how many constraints we can put on these parameters before submitting to the minimization procedure. So we can easily constrain the normalization of this function by requiring that once plugged in this expression, the good transversity fulfills the Sofer bound at any scale. So this is easy. And then the second constraint we can put is on this parameter, capital A, which drives the behavior of this parametric function at the low x. So if you look at the low x behavior, this goes like x to the capital A. And we can also estimate the low x behavior of the analytical expression of the Sofer bound. So this goes like a power of x to this small a, which is a calculable parameter. And therefore, at the end of the day, your low x behavior of transversity is just a power law that involves both two parameters, the free parameter and the calculable one. And this is crucial in order to compute our tensor charge, because, for example, if you wanted to have a finite tensor charge, this combination must be strictly positive, otherwise everything is going to diverge. Okay? And then we can look for other sources of constraint. For example, if you look at the work of Alberto Accardi and Alessandro Battetta, where they try to study extraction of transversity at twist 3 in inclusive DIS, as a byproduct, they got a new version of the Boot-Karkotikam sum rule, where they got an additional term, the violation of this sum rule, related to this Melly moment of order -1 of the transversity. And again, if you want this violation to be finite, you have to impose a condition on the combination of the two parameters, which is stronger than the previous one. Alternatively, you can look at work of Yuri and Matthew Sievert that was recently released. They studied the law X behavior of transversity in the dipole picture, and they came up with a power law where the exponent involves the alpha strong and the number of colors considered. And if you study this exponent at our initial scale of 1 GeV, this is equivalent to put these constraints on our parameters, so that the combination of the two parameters must be of the order of 1, which is not in contradiction with the other choices. So at the end of the day, we made this choice. So we took this combination to be greater than 1/3, which means that we want the transversity to go to 0 like x to the minus 2/3 at least, or even faster. And oops, sorry. And this is important because for the purpose of calculating the tensor charge, because when we numerically compute this integral, we never compute the integral between 0 and 1. We start from a minimum value of x. And in the case of our MSTW parameterization, the minimum value of attainable x is 10 to the minus 6. And therefore, we are able even to estimate the error we make in neglecting the part of the integral between 0 and this minimum x, which is in this condition is of the order of 1% of the total value. So the error is small. On the contrary, we have a very large source of uncertainty coming from the unpolarized di-hadron fragmentation function, capital D1, because we control the quark channel using the Bell data, but we don't have any clue on the glue, because we are working at the leading order, and the glue in the plus and minus enters only in the next leading order level. And moreover, we don't have data on multiplicities in the proton-proton collisions. So basically, we decided to explore 3, let's say, wild scenarios. So the first one is where we take the gluon at the initial scale to be 0, which means that all the gluons are created radiatively, so through the evolution. And on the other hand, the other extreme scenario is that the gluon decay at the initial scale is equal to the upward. Okay? And then we explored also an intermediate choice where the gluon is equal to 1/4 of the upward, which more or less corresponds to the size of the gluon fragmentation function in the single hadron case. Okay? Good. So far for the theoretical, I would say, systematic errors, uncertainties. Now, what do we do with the statistical errors? So we described them with the usual bootstrap method, which means basically we take the experimental data and we alter them, introducing a Gaussian noise within experimental variance. So we create a replica of the data and we fit it. And then we repeat the procedure 50, 100, 200 times, and we stop when the envelope of the replicas reproduce the average and the standard deviation of the envelope of the replicas reproduce these original experimental points. In our case, it happens after 200 replicas for each of the gluon scenarios that I have considered. So in total, I have 600 replicas. Okay. Now, for each bin, experimental bin, I exclude the largest, smallest 5% of this replica, and I build my 90% uncertainty band. So if the things would be distributed as a Gaussian, this would correspond to the 2 sigma standard deviations. Moreover, more importantly, the replica adjust themselves in a sense, so they automatically include correlations between the experimental data. Okay, so let me come to the results. First, I show you results that Alessandro and I published in this paper, and they are obtained using the experimental points that I was mentioning to you. In particular, we have the CDIS data from compass dynamics from proton and deuterium target. And we have data from proton-proton collision started at s equal to 100 GeV squared for the invariant mass distribution of the final pion pair at the forward and backward rapidity, for the PT distribution of the pair, backward and forward rapidity, and for the rapidity distribution itself. Now, in total, we have 22 points from semi-inclusive DIS, 24 points for stars, which are not all independent, and we take into account this. As I said, we have 10 global field parameters, so at the end of the day, we have 22 degrees of freedom. Here you see the histograms of the 600 chi-squares each chi-square for each replica, and compared with the corresponding probability density function for the chi-square distribution with the same number of degrees of freedom. And you see that basically, if we had hypothetically a chi-square per degrees of freedom equal to 1, then the area under this red curve should perfectly overlap with the area covered by this histogram. So this is a sort of graphical representation of the fact that we do not get chi-square per degrees of freedom equal to 1, but we get 1.76 plus minus 0.11. Okay? And most of this chi-square contribution comes from the tension between our replicas and the star data for the distribution at forward rapidities. Okay, so how do the transversity look like? So this is a transversity multiplied by x as a function of x at 2.4 GV squared for the valence half quark. The blue lines are the Sofer bounds. And the light blue band is the result of our global fit, compared with this pink band in the background, which is a result of our old fit where only semi-inclusive EIS data were used. So if you look at this plot, you basically can appreciate the impact of including star data on proton-proton collisions, which brings much more precise results for the half quark. Incidentally, this pink band also almost entirely overlaps with the result of the extraction of transversity using the Collins effect. So you can use this plot also to compare our global results from our global fit with the extraction of the Collins effect. So we can safely conclude that at the moment, our result for the half quark is the most precise available. This result is also stable because if we change all the scenarios for our gluon di-hadron fragmentation function, the results will basically unchanged. So far, so good. And unfortunately, this is not true for the down quark transversity. So these are the results for the down quark transversity with the same notations as before. And you see that if I move from one scenario to switching on all other three possibilities, you see that the uncertainty band from the down quark transversity enlarges so much that I'm not even able to say which is the sign of the down quark transversity. Okay, and this happens because in the proton-proton collisions, the gluon is there in leading order already, and the up and down are weighted have the same weight. While in the semi-inclusive EIS, the gluon happens only in the next leading order, and the up quark is weighted 8 times more than the down quark. Okay, so that's why the down quark is much more sensitive to what we do for the gluon. In any case, the bottom line here, the message is that we have to do something to contribute to this channel because this affects a lot our extraction. Okay, what happens for the tensor charges? So these are the results for the up tensor charge, the down tensor charge, and the iso-vector combination. So our result is this blue point with label 3 here and here. And again, it's a result of a global fit from data on semi-inclusive EIS and proton-proton collisions. You see, the other colored points are the results where the transversity is extracted using the Collins effect with only semi-inclusive EIS data. So in the red point is with the label 5 is the results from Alexei, John Bokang in the TMD framework. The magenta point with the label 6 here is all the results from the Torino group in the context of the extended pattern model. And the green point here is the result of the JAM collaboration of Hugo and collaborators, where they used the Collins effect, but they also inserted the constraint to reproduce the iso-vector results from lattice. Okay? And this brings me to comment the black points here with label 8, 9, 10, and 11. These are the results from some lattice collaborations, the most recent ones that I found in the literature. And with label 8, I indicate the results from the PMDME collaboration. With label 9, the results from the ATMC. And these two are the only ones that compute also disconnected diagrams, and therefore they are able to address the separated flavor results for the tensor charge for the up and the down separately. And then with label 10 and 11, I list also the results from our QCD and LHPC collaborations. So you see that the size of these error bars from lattice are I would say suspiciously very small. And I say suspiciously because, for example, for the case number 9, ATMC, we know that this work is done using only one lattice spacing. So there is no systematic study of the systematic errors related to the continuum extrapolation or to the extrapolation to larger volumes and so on. So these error bars here are definitely very underestimated. Okay, anyway, we look at the results. You can say that, for example, here phenomenology agrees, but disagrees with lattice. Here there is an agreement, except for the jump results. And here again, the phenomenology seems to agree, but disagree with lattice, with the jump. So in general, yes?
As you know, there are so many quark model predictions, and I think the value is much larger than the one we obtained.
Yeah, I deliberately excluded model the calculations.
Yeah, so just to have, would you notice that give a statement that basically the quark model fails dramatically?
Well, I'm not making
because at some point, before we had experimental information about it, it was thought that the tensor charge would be better amenable to a quark model than the Coulomb. So the EIC. Turns out that's not the case.
No, yeah. Actually, my focus here is a little bit different. It is what I was about to say is that looking at this, you would conclude in general there is no simultaneous compatibility between lattice and phenomenology, which is even more important, I would say, that commenting results from the quark model. And this is quite disturbing in a sense. And when I say simultaneous, I mean if I consider all three components of the tensor charge up, down, and as a vector combination. Okay, so a few months ago, Compass people asked me to do an exercise to test what happens, which is the impact in my global fit using a set of pseudo-data, where they calculated the projection of the error bars from a future measurement of the repeated measurement of the neutron target, this is that we have in 2021. You see the points here in magenta. These points are taken exactly at the same beams that where the older measurement of 2004 was taken, which are the black points here. But you see that with a significantly smaller error bars. And in this exercise, I decided to choose the average, the central points of these beams, corresponding to the results that I got in my global fit of the black data. So in other words, this exercise is to test which is the relative precision of in gaining in precision by including this new set of pseudo-data without saying anything about the position of the central value of these points. So you see an effect of including this pseudo-data on transversity. So now the pink band is the result of the global fit that I showed you in the previous slides. And the light blue band are the results of including this compass pseudo-data. You see that you have a dramatic increase in precision for the down part of transversity. It is less evident in the proton case, but if you carefully look at the ratio between the width of the uncertainty bands, which is shown in this plot below, you see that you have, where there are data, you systematically have an increase in precision also for the up quark. And for some X, this increase is of the order even of 20–25%. Okay, so what happens for the tensor charges? Again, consider the blue points, which are the results of my global fit. And the orange point is what I get if I include this concept pseudo-data. So you see there is quite a significant reduction in error bars. Here as a reference, I quote also the projection from solid, okay, that will really change life if this reduction of the error bars will be confirmed. And this reduction in precision of the orange point is basically in the isovector components comes mostly from the down quark component, which is really much more smaller error bars than before, while for the up quark nothing basically changes. And again, you can explain this by thinking that in the deuteron, because of isospin symmetry, the up and down quarks are weighted similarly, while in the proton case, again, the up quark is weighs 8 times more than the down quark. So data on the deuteron, new data on deuteron will affect more the down than the up quark. Okay, now this this exercise doesn't change, as I said before, doesn't say anything about the position of the central points of this data, just shows you what is the relative precision. So the statement about the simultaneous compatibility between phenomenology and the lattice is still there, the issue is still there. This is a way to quantify the precision, the more precision we gain, including compass pseudo-data. So we go from a chi-square predictive of 1.76 to 1.12. Okay, and now the histograms of the 600 chi-square do much better have a much better overlap with the ideal probability density function corresponding to the new number of degrees of freedom. Okay, now. Next, I did this exercise, so I wanted to test if there is a statistical compatibility between the result of my global fit with the numbers from lattice for the isovector tensor charge. So basically, I repeated the exercise that Nobuo did with the Collins effect in this paper, this green point here. And I repeated the fit, imposing the constraint that my replica have to reproduce the value of the lattice value for the isovector tensor charge. Now, the question is that which is this value actually? If you look in the literature, there is the flag collaboration proposed a procedure to calculate the average value of this isovector tensor charge out of several calculations of several groups. The problem is that the proposed procedure takes the central value of each calculation and weights it using the inverse of the width of the quoted errors. So this means that all calculations that underestimate the error will become more important with respect to other ones, which is not what we want. And therefore, I decided to go by brute force, and I took the minimum and the maximum values of these calculations, and I built a sort of uncertainty envelope here, and I computed the central point and the width. And I came to this number, and this is not the constraint that I inserted in my global fit. So my replica are constrained to reproduce, when I calculate the isovector tensor charge, are constrained to reproduce this number. Now, this is the result, and it is identified by the brown point here with label 2. This is for the isovector component, which, of course, by construction is consistent with the lattice. This is the result for the down quark, and this is the result for the up quark compared to our previous global fit, which is the blue point. And you see that the consistency with the lattice in the isovector component comes at the price of reducing the value of the down quark, even destroying the previous agreement that we had between lattice and our results, while nothing basically changes for the up quark. So the general comment is that, okay, we have compatibility here, but we still have disagreement here, and now we have disagreement also for the down quark. So we didn't solve the issue, in other words. And of course, this situation is reflected in transversity, where now the up quark is basically unchanged, but the down quark transversity goes to lower values, particularly for lower x, in order to have these tensor charges much smaller. Okay. And not only, the second drawback of this analysis that we worsen our chi-square is that in fact we go from 1.76 to 1.82, and we have a poor overlap with the ideal situation. Okay. Next and final step of the exercise, I try to insert in my global fit the constraint to reproduce all the tensor charge results from lattice, not only the isovector component, but also the separated flavor up and down. And again, I built the central values, the average values for the up and down tensor charges from lattice with the same procedure as before, and I came with these two numbers. Okay, the results now is identified by this pink point with label 1 here, here, and here. And you see that the error bars are now very reduced because of these constraints, and now you have compatibility here, here, and also here. obtained by raising dramatically the results for the up quark. Now, we have compatibility, but we have to pay a price. And the price we pay is that the chi-squared becomes really bad. We go to from 1.76 to 2.29. And basically, there is no overlap between the area covered by these histograms and the ideal situation. Okay? So in other words, we do have a set of replicas that are compatible with the results from lattice, but this combination is statistically very unlikely. Okay? Now, as I said, here, in order to reach this compatibility, we have to increase a lot the result of the tensor charge with the up quark. So this means that at the level of transversity now, we really want a transversity which is definitely larger than before, also in the range where the data are, and the X range of the data are. And this means that we are altering also the truncated tensor charge values. Okay, so and this is the integral restricted to the X range where there are data, where typically you would like to have stability. And while you have stability for the down quark component, really you destroy it in the up quark sector. Okay, and again, the notation as before, this in red is the result of a calculation of an XA, which was in perfect agreement with our global fit, and which is now not in agreement with this new results of the fit, including those constraints. Okay, so what can we do further? Of course, I have a certain set of data still to include in the fit, as I said before. For example, I have to redo the fit of the Bell data of the unpolarized cross-section in order to extract the unpolarized quark decay, not from the Monte Carlo, but directly from data. And I have also to consider the star data at a larger energy, so 500 GeV squared, and possibly when they will be finalized, also the data 200 GeV squared from the 212 run. Here you see, well, you can see the uncertainty band here. Here you see this the variant mass distribution of the two pairs coming from the 500 GeV square and the 200 GeV square and the SE from the run in 2012. And here you should see an uncertainty band similar to this one. These are predictions from our fit based on only semi-closed DIS data, but in any case, they are predictions that really fall happily on this data, so are encouraging us to include this in the future release of the global fit. The problem with all this data is that they all lie within the X range, which is currently covered by the data I've been using in the present version of the fit. And this means that if I want to improve from the phenomenological point of view, the calculation of the tensor charge, this data will not help me very much, because in order to really go beyond, step beyond, I would need the data with the data that allow me to enlarge the X range in order to more safely calculate the many moments of transversity, particularly at large values from JLab. I will need data from JLab 12, and the smaller value of X, I will definitely need data from EIC, unless we find other theoretical constraints that drive my extrapolation. Okay. Okay, with this I conclude. I showed you the first example of a global fit of di-hadron inclusive data, so in semi-inclusive DIS and PP collisions that lead to extraction of transversity as a collinear PDF. So the inclusion of star data help us increase the precision of the up quark results, while we have large uncertainties for the down because of the uncontrolled gluon component of the di-hadron computation function. We do not find apparent simultaneous compatibility with our results and the results from the lattice for all components of the tensor charge. If we add the pseudo-data from COMPASS for future data, future measurement of the deuteron, we increase the precision, but we do not alter, particularly for the down quark, but we do not alter this scenario on the tensor charge. And if we fit we force our fit to reproduce the lattice results for the isovector tensor charge, or even for the up and down components, actually we can find some combination of replica that lead us to compatibility, but at the price to have a very bad chi-square, and therefore to have a combination which is statistically not very favorable. So I think that there is an issue at the moment between between lattice and phenomenology. And the only thing we can do from the phenomenological side is to explore new constraints to enlarge the set of X range covered by the experimental data.
So the lattice groups, what technique are they using? Are those moments? Are those quasi-PDFs?
No, I'm talking about moments. I didn't quote the quasi-PDFs. There is a recent calculation that appeared a few days ago on the archive. They have a very precise high X trend, but all quasi-PDFs are plugged by very large uncertainties and small X. And according to our experience, this means that they are not yet in a condition to reliably calculate the tensor charge, integrating that PDF, because the low X part of the low X values are really important in precisely determining the tensor charge. They are very large uncertainties.
But presumably the moments are also not very sensitive to X.
Yeah, sure, but if moments you can directly calculate the matrix element of a local operator, so you don't. You don't have to go through the quasi-PDFs. Yes.
If you go back one slide,
Yes.
so if we could provide data in PT in the X range between 10 to the minus 1 and 1 for IFF, with a forward upgrade, of course, it produces, because we go to a rapidity of 2.5 before, and we haven't actually looked to the end cap, which we could also do with the ITPC upgrade. Would that help to constrain the Deuterium better?
If you remember 2 weeks ago when I gave part of this talk, Fang commented that according to their experience, they see a sensitivity of the order of 60% of the integral to the values of transversity at very large X. Yeah. Which sounds to me a little bit large, okay, but fine. Anyway, certainly useful.
Okay, and especially with Deuterium, because the Deuterium is much better constrained in proton-proton because of the non-charge rating. So that could be, and that is something which we could do. Okay.
Okay, good.
Yes, looks like from your analysis, the tension with that seems real and seems not easily get away. That's maybe not too big tension yet. I have a question about your large X part. You use this surface bound. I remember early days you were showing the di-hadron data has some tension with this. Do you try to not use the bound? What will be the consequence now?
First of all, it was not my data. There was actually only two beams from compass on the Deuterium. But you know, that was a statistical noise, because introducing data from star, the statistical relative weight of those importance of those two beams diminishing, and as you saw, basically all the exotic trend of our replicas to saturate the super bound has disappeared. But maybe I can. Where is it? Yeah, you see this pink band was our result of our previous fit with only semi-closed DIS data. You see that all replicas wanted to saturate the super bound pretty early, okay, in X, where the experimental data are, and this trend was driven by those two bins. But now, including data from start, this trend has basically disappeared. You see the results of the global fit is this blue band. Very large because of the uncertainty of the gluon decay, but this strange behavior has basically disappeared. So this was an artifact, maybe due to the fact that our functional form is very, very flexible. I don't know. Anyway, now it's no longer there. Say, coming back to the Sofer bound. Well, this is a philosophical question. So. Ralston, I guess, said made a statement that in principle one could explore what happens going beyond, and maybe there is interesting physics to explore. I don't know. Actually, I would say I'm a bit reluctant because given that such a small amount of data available for this analysis, if I give up also all the possible constraints, theoretical constraints that I can have, I'm really lost. I mean, I can go everywhere. So I would have replicas that basically fill all the phase space, and then I gain anything.
Use nested sampling.
Huh?
Use nested sampling, it converges quickly.
Yeah, okay.
It's a problem because the replicas don't converge.
Well, in principle, then I can go to with neural networks, but the things would become even more messy because neural networks were really they are even more less constrained than our functional. At least we have a functional form at the beginning. Then we use replicas, but the neural networks don't have even this bias, so you clearly go everywhere. You have constraints from data or from other sources.
I'm concerned about the increase in the chi-square degree of freedom the star data. Is an indication of tensions that we have, there is some model dependence that maybe is underestimated?
Well, I think that is probably due to the fact that the tension is there, and it is mostly, as I said, it's mostly due to the PT distribution from star forward rapidities. But I guess it's mostly has to do with the fact that our theoretical description is still preliminary and not very sophisticated. So remember that we are still a leading order. So we are planning and working on to improve the next formula at the next leading order level. But this, of course, it takes time because we have to basically re-extract the di-hadron permutation functions in the next leading order with the next leading order description. And therefore, we have several steps before coming to the global field. I guess that this is probably the real source of this tension, because otherwise I would not see any real reason why that particular subset of the star data would contribute so much to the chi-square.
We come back at 4:30 and there will be a discussion session.